our modern world runs on computation. From the smartphones in our pockets to the global networks that connect us, classical computers process information with incredible speed. Yet, even the most powerful supercomputers face fundamental limits. There are problems in nature, in the very fabric of the universe, that are simply too complex for any classical machine to ever truly simulate or solve. Imagine trying to predict the behavior of every atom in a complex molecule, or breaking codes that would take the age of the universe to crack. These are the impasses that human ingenuity now confronts, demanding a radical new approach. For decades, the path forward seemed clear: make classical transistors smaller, faster, more numerous. But as we approach the atomic scale, the rules change. The universe at its most fundamental level operates not on predictable, binary logic, but on the strange and counterintuitive principles of quantum mechanics. This deep understanding has opened a new door, not just to faster computation, but to an entirely different kind of computation. This is the realm of quantum computing, a technology that promises to unlock solutions previously thought impossible. At the heart of every classical computer is the bit, a binary unit of information representing either a 0 or a 1. It's definitive, unambiguous. A quantum computer, however, relies on the qubit. Unlike a classical bit, a qubit can be 0, 1, or, thanks to a phenomenon called superposition, a combination of both simultaneously. This isn't just a clever trick, it fundamentally changes how information can be stored and processed, allowing for an exponential increase in computational power with each added qubit. Imagine a coin spinning in the air. Before it lands, it's neither heads nor tails, it's a dynamic combination of both possibilities. This is a simplified analogy for superposition. A qubit exists in a blur of potential states until it's measured. When measured, it collapses into a definite 0 or 1. This ability to explore multiple possibilities simultaneously is what gives quantum computers their immense parallelism. Instead of trying each solution one by one, a quantum computer can explore many paths at once, a crucial advantage for complex problems. Beyond superposition, there's an even stranger quantum phenomenon: entanglement. When two or more qubits become entangled, they become intrinsically linked, no matter how far apart they are. The state of one instantaneously influences the state of the others. If you measure one entangled qubit as a 0, you immediately know the state of its partner, even if it's light years away. Albert Einstein famously called this spooky action at a distance. This correlation allows quantum computers to perform incredibly complex operations, creating vast computational spaces. The combined effect of superposition and entanglement is what grants quantum computers their extraordinary potential. While a classical computer with n bits can represent only one of 2 to the power of n possible states at a time, a quantum computer with n qubits can represent all 2 to the power of n states simultaneously. This means that adding just a few more qubits can exponentially increase the computational power, far outpacing any classical machine. For certain types of problems, this isn't just faster, it's a qualitative difference, opening up entirely new problem-solving landscapes. So, what kinds of problems necessitate such a radical shift? Consider drug discovery. Simulating how a new molecule interacts with a protein involves an astronomical number of possible configurations, a task too complex for even the most powerful classical supercomputers. Or materials science, designing novel compounds with specific properties at the atomic level. Financial modeling, optimizing complex logistical networks, or even climate change simulations, these all involve variables and interactions that grow exponentially, quickly overwhelming traditional methods. The concept of quantum supremacy emerged as a milestone, referring to the point where a quantum computer performs a computational task that is practically impossible for the fastest classical supercomputer. In 2019, Google announced achieving this with their Sycamore processor, solving a specific, highly technical problem in minutes that would have taken the world's most powerful supercomputer thousands of years. While this particular problem wasn't inherently useful, it demonstrated the potential, a powerful proof of concept for the new era of computing. Beyond theoretical milestones, the race is on for practical quantum applications. In chemistry, it promises to revolutionize drug design by accurately modeling molecular interactions, leading to new medicines and therapies. In materials science, it could unlock superconductors at room temperature or batteries with unprecedented energy density. Quantum computing also holds immense promise for artificial intelligence, optimizing machine learning algorithms for pattern recognition and data analysis far beyond current capabilities, accelerating breakthroughs across numerous scientific and industrial fields. One of the most significant implications of quantum computing lies in cryptography. Many of the encryption methods protecting our online data, from banking transactions to national security secrets, rely on mathematical problems that are currently intractable for classical computers. Shor's algorithm, a quantum algorithm, theoretically allows a large-scale quantum computer to break these widely used public key cryptographic systems, like RSA, in a fraction of the time. This poses a serious future threat, driving urgent research into post-quantum cryptography. Building a qubit is an immense engineering challenge. Unlike classical bits, which are robust and relatively stable, qubits are incredibly fragile. They rely on delicate quantum phenomena that are easily disrupted by environmental noise. Scientists are exploring various physical implementations, from superconducting circuits cooled to near absolute zero, to trapped ions suspended in electromagnetic fields, or even topological qubits, which aim for inherent stability. Each approach has its own unique set of advantages and formidable challenges in scaling and error management. Many leading quantum computing architectures, particularly those based on superconducting circuits, demand extreme conditions. These qubits must be isolated from nearly all external interference, meaning they operate at temperatures colder than deep space, just a few thousandths of a degree above absolute zero, minus 273.15 degrees Celsius. Achieving and maintaining such temperatures requires complex, multi-stage dilution refrigerators, sophisticated engineering, and a constant expenditure of energy. This cryogenic requirement alone presents a monumental hurdle to scaling these machines. Even with extreme cooling and shielding, qubits are susceptible to decoherence. This is the loss of their delicate quantum state, their superposition and entanglement, due to interaction with their environment. Any stray vibration, temperature fluctuation, or electromagnetic field can cause a qubit to collapse prematurely, destroying the computation. Maintaining quantum coherence for long enough to perform meaningful calculations is perhaps the most critical challenge facing quantum engineers. It's like trying to maintain a perfectly balanced house of cards in a hurricane. Because qubits are so fragile, they are highly prone to errors. A single bit flip in a classical computer is often easy to detect and correct, but in a quantum computer, an error can spread rapidly and corrupt the entire computation. Classical error correction relies on redundancy, making multiple copies of a bit. Quantum mechanics forbids copying an unknown quantum state, necessitating far more sophisticated techniques. Quantum error correction requires many physical qubits to encode a single, logical, error-corrected qubit, vastly increasing the resource requirements. Building a useful quantum computer doesn't just mean having a few good qubits, it means having hundreds, thousands, or even millions of stable, interconnected, and error-corrected qubits. Current machines often operate with tens or a few hundred physical qubits. Scaling these systems is not merely a matter of adding more components. Each additional qubit increases the complexity of control, wiring, and isolation exponentially. This scaling conundrum is a fundamental limit that pushes the boundaries of our current engineering capabilities and manufacturing precision. We are currently in the noisy intermediate-scale quantum or NASQ era. This describes quantum computers with 50 to 100 qubits that are too small to implement full error correction and are susceptible to noise. While these machines can perform calculations beyond classical capabilities for some specific tasks, their limited coherence times and high error rates prevent them from solving truly universal, complex problems. The NASQ era is a critical stepping stone, allowing researchers to develop algorithms and hardware, but it highlights the immense gap to truly fault-tolerant quantum computing. Hardware is only one piece of the puzzle. Developing quantum algorithms is an entirely new field, requiring a different way of thinking about computation. Existing algorithms like Shor's for factoring and Grover's for searching demonstrate the power, but discovering new algorithms for practical applications is a major research area. Furthermore, programming these machines requires specialized quantum programming languages and compilers that can translate abstract algorithms into precise control pulses for finicky qubits. This is a nascent field, ripe for innovation and discovery. Beyond the technical challenges, quantum computing pushes against the very limits of our intuitive understanding of the universe. The principles of superposition, entanglement, and measurement defy classical common sense. Designing and debugging quantum systems requires a deep dive into quantum mechanics, a field still riddled with its own mysteries and interpretational debates. Our human brains, evolved to perceive a classical, macroscopic world, struggle to grasp the probabilistic and non-local nature of the quantum realm, making innovation inherently challenging. Nations and corporations worldwide are locked in an intense race to achieve quantum advantage. Governments recognize the strategic importance for national security, economic competitiveness, and scientific leadership. Tech giants like IBM, Google, Microsoft, and Amazon are investing billions, alongside numerous well-funded startups. This competition fuels rapid progress but also highlights the immense resources and expertise required. It's a testament to the perceived transformative potential of this technology, a new frontier demanding global collaboration and innovation. The current cost of building and operating a quantum computer is astronomical. The specialized materials, extreme cooling systems, highly precise control electronics, and a team of world-class quantum physicists and engineers make it an incredibly expensive endeavor. Moreover, the infrastructure required is significant, from dedicated shielded laboratories to advanced manufacturing facilities for superconducting chips. This high barrier to entry means that access to quantum computing is currently limited, posing questions about equitable access and who will ultimately benefit most from this technology. While the qubits themselves consume very little energy once at operating temperature, the supporting infrastructure for quantum computers can be quite power-intensive. The powerful refrigeration units, control electronics, and classical supercomputers needed to manage quantum calculations require substantial energy. As quantum computers scale, so too will their energy demands. Researchers are actively working on more energy-efficient designs and alternative qubit architectures, but the energy footprint remains a consideration for widespread adoption and environmental sustainability. It's crucial to temper expectations. Quantum computers are not simply faster classical computers, nor will they replace them for everyday tasks. They won't browse the internet faster, run word processors, or render video games. Their power is specialized, suited for specific types of problems that exploit quantum phenomena. For most computational needs, classical computers will remain superior due to their stability, ease of programming, and cost-effectiveness. The future of computing is likely a hybrid model, where quantum coexists with, and augments, classical systems. The most promising path forward involves hybrid quantum classical computing. In this model, classical computers would handle the bulk of computational tasks, offloading only the most quantum-intensive portions to quantum processors. This leverages the strengths of both paradigms, the robustness and versatility of classical machines, combined with the unparalleled power of quantum for specific, intractable subproblems. Developing the interfaces and algorithms to efficiently manage this interplay is another significant research challenge, but it represents a pragmatic approach to unlocking quantum advantage sooner. As with any transformative technology, quantum computing raises profound ethical questions. The ability to break current encryption schemes necessitates global cooperation on post-quantum standards to avoid a catastrophic security crisis. The potential for advanced AI could accelerate automation, impacting jobs and societal structures. The immense power concentrated in a few hands could exacerbate global inequalities. These are not distant problems, they are discussions that must begin now, guiding the responsible development and deployment of quantum technologies for the benefit of all humanity. Despite the incredible progress, truly fault-tolerant, large-scale quantum computers are still decades away. The journey from scientific curiosity to practical utility is long and arduous, filled with unforeseen challenges and incremental breakthroughs. It demands sustained investment, relentless scientific inquiry, and a global community of researchers pushing the boundaries of what's possible. It's not a single race to a finish line, but a marathon of discovery, requiring patience, persistence, and visionary leadership to navigate the complex landscape of quantum mechanics. The limits of human technology is not a static barrier. Throughout history, humanity has constantly redefined what is possible. From harnessing fire to splitting the atom, our capacity for invention, problem-solving, and adapting to new paradigms has been our greatest strength. Quantum computing embodies this spirit. It forces us to confront the very nature of reality at its smallest scales and build machines that operate according to rules that seem alien to our everyday experience. This endeavor is a testament to our insatiable curiosity. The quest for quantum computers represents one of humanity's most ambitious scientific and engineering undertakings. It challenges us to manipulate individual particles at fundamental levels, to maintain coherence in the face of quantum chaos, and to design algorithms that exploit an entirely new computational paradigm. It's a frontier that promises not just faster calculation, but deeper insights into the universe itself, potentially unraveling mysteries in physics, chemistry, and biology that have eluded us for centuries. Every challenge, no matter how immense, presents an opportunity for breakthrough. The history of science is replete with problems once deemed insurmountable that were eventually overcome by human persistence and ingenuity. From new material sciences that can better isolate qubits, to novel error correction codes, to more efficient cooling methods, the pace of innovation in quantum computing is accelerating. Each year brings new discoveries and pushes the envelope of what we thought was technologically feasible, keeping the promise of a quantum future alive. When quantum computers reach maturity, their impact on society will be profound and far-reaching. Imagine personalized medicine tailored to your unique genetic code, materials that make existing technologies obsolete, or AI systems with intelligence previously confined to science fiction. The ability to simulate complex systems with unprecedented accuracy could help us tackle climate change, design sustainable energy solutions, and even understand the origins of life. The quantum revolution promises to redefine our relationship with technology and the natural world. The journey to building powerful quantum computers is as significant as the destination itself. The scientific understanding gained, the engineering innovation spurred, and the new computational paradigms discovered along the way will undoubtedly yield unforeseen benefits. It's a journey that challenges our assumptions, expands our knowledge, and forces us to confront the deepest mysteries of the universe. Even if universal fault-tolerant quantum computers remain a distant goal, the research itself is fundamentally advancing human understanding. The scale of the challenge in quantum computing is truly monumental. From cooling individual qubits to fractions of a degree above absolute zero, to precisely controlling their delicate quantum states with microwave pulses, to interconnecting thousands or millions of them without introducing errors, every step demands extreme precision and innovative solutions. It's a testament to human ambition that we are even attempting to build machines that operate at such a fundamental, fragile level, pushing the very definition of what technology can achieve. The pursuit of quantum computing is driven by a deep scientific imperative to understand and harness the fundamental laws of nature. It's not merely about creating faster calculators, but about building tools that reflect the universe's own computational language. By delving into this quantum realm, we gain not only a powerful new technology but also a more profound understanding of reality itself, bridging the gap between theoretical physics and tangible engineering. This quest embodies the very essence of scientific exploration. For centuries, many scientific and technological feats were deemed impossible until human ingenuity proved otherwise. Flying, reaching the moon, instant global communication, all once seemed like fantasy. Quantum computing confronts a similar set of seemingly insurmountable obstacles. But the very existence of quantum mechanics in nature suggests that these impossible computations are, in fact, possible. The question is not if they can be done, but when, and by what means humanity will finally master them. Despite the immense hurdles, the progress in quantum computing is undeniable and inspiring. Each passing year, researchers achieve new benchmarks in qubit count, coherence times, and error reduction. The sheer dedication and brilliance of thousands of scientists and engineers worldwide offer a glimmer of hope that these limits of human technology are not permanent walls, but rather temporary frontiers to be pushed back. The dream of unlocking the full potential of the quantum realm is slowly, but surely, becoming a tangible reality. In the end, quantum computing is not just about technology, it's about the human endeavor. It's a reflection of our innate drive to explore, to understand, and to overcome challenges that seem beyond our grasp. It encapsulates our collective ambition to build tools that extend our capabilities, allowing us to perceive and interact with the universe in ways previously unimaginable. As we continue this profound journey into the quantum, we are not just building machines, we are expanding the very definition of what it means to compute, and perhaps, what it means to be human.